So here's what I call the volumetric formula. So this is just this simple formula that you would maybe use to calculate recoverable hydrocarbons. You can see there's a number of input parameters. It goes what's called gross rock volume. What we're trying to do is define within this structure under the ground how much oil and gas it can contain. And once we know how much is in the oil and gas structure, how much of it could we produce. So we've got things called gross rock volume. That's the volume of the field. Okay, the volume of rock that's trapping the hydrocarbons. The net to gross, what that means is not all of that container or that trap is going to be what's called reservoir. It's going to be reservoir and non-reservoir. So not all the volume can count and hold all hydrocarbons. So that's a sort of a ratio that reduces that volume. Then we have to apply what's called the porosity to it. So when you've got a reservoir, you actually have to have space for the oil and gas to be contained. Okay, so you have to have space between the grains, if it's a sandstone, that can hold oil and gas. If it's got no porosity, it can't hold on the oil and gas. The only proviso is that we could talk about non-conventionals, but that's not the topic for today. So in conventional sense, we've got to have pore space. But the pores have to be filled with hydrocarbons because there's obviously a gradation from oil down to water. So we have to actually measure the saturation of oil, the ratio of oil to water in the pore space. We have to correct it because it's under temperature and pressure, it's at depth. So we have to do some corrections to bring it up to surface conditions. So I won't explain formation volume factors, but they need to be applied to the calculation. And the final, so if we multiply everything through to that stage and stopped before what's called RF, that would be the volume of oil that's in place, or gas in place. That's what's in the container, okay? We now have to work, well, how much of that oil and gas in the container will actually come to the surface if we drill wells into it and allow it to flow. And the final thing there, which is where we put a lot of effort, is maybe the last part of that equation, but where a lot of effort goes into is what's the recovery factor. And the recovery factor is a bit not simple to define because it's almost linked to how you're going to develop it. So there's a bit of a linkage to the plan of development. But effectively, we need to assess how much percent of that volume is going to come to the surface. So in a simple primary recovery scheme for oil, you could get 30 or 40% of that volume of oil in the ground out to the surface. So you're leaving, by definition, 60 or 70% of the oil in the ground. You just can't get it out, okay? Under a simple, say, primary recovery scheme. All right? So that's the volumetric formula. Now, unfortunately, every single element in there, of course, is uncertain. We don't know how big the container is. We may only have one well, so we don't know what the net to gross ratio is, or the porosity, or the saturation. We just got one point, one data point. So rather than try and guess at ranges, what we might do is we replace or represent the uncertainty with a distribution of values. So you can see here I've shown you distribution. All the distribution says is how low can the value be to how high it could be, and the shape of the distribution and the height of the distribution tells you effectively the relative probability of different values. So where you get to the peak there, that could be the most frequently occurring value, okay? The modal value. So if I was a best guess, that's what I think it could be, but it could be as low as this or as high as that. And the shape of the distribution defines how relative the probability of one value to other is. So we spent a lot of time doing that, and then we take those values and we apply it into a modeling technique called Monte Carlo simulation.